a plus bi. This channel is all about complex numbers, and in this video we're going to be solving another radical equation. This is actually a pretty interesting equation because you'll see in a little bit we have z times the square root of z equals -2 plus 2i, and we're going to be solving for z values. I'll be presenting two methods, and let's start with the first one. The results from the two methods are going to be somewhat different, and definitely we can always talk about why that's happening. But regarding the square root of z, I'm going to stick to the principal square root so that we have an agreement on what roots we're looking for, okay? So first method is going to use the polar form. I'm going to write the z as r e to the I theta. From here, if you take the square root, it's going to be square root of r times e to the power I theta over 2. Of course, there's another one that we can add pi to the argument, because when you square them, they'll give you the same number. But which one is the principal square root? I'm going to assume that it's this one. But you can always check your results. And there's probably a way to avoid this issue, but I like to just dive in, do it, and then later on check my work. So let's go ahead and evaluate z root z from here. I'm going to go ahead and multiply r root r and then add the arguments, and that's going to give me 3i theta over 2. And I expect this to equal -2 plus 2i. So from here, can I find r and theta? And the answer is yes, if you write the right-hand side in polar form as well. So let's do it. This is going to stay the same. And the right-hand side, if you find the argument, it's going to be 2 root 2 square root of 8. And inside, you're going to have root 2 over 2 with a negative sign plus root 2 over 2 multiplied by I. Now, the tricky part is writing the right-hand side in polar form using r and theta for the right-hand side, of course. Not the same r and theta that we have currently, but 2 root 2. And think about it. This is the cosine of an angle, and this is the sine of an angle. First of all, realize we are in the second quadrant because cosine is negative, and the angle is 3 pi over 4. Why? Because of the values of cosine and sine, their absolute values are equal. So it should be like pi over 4 or multiples, right? So we can write it as e to the power 3i pi over 4, which is I times 3 pi over 4, right? Cool. Now by comparing the moduli, such an interesting word, right? We get that, okay, r equals 2. Nice. And by comparing these two things, we get 3i theta over 2 equals 3i pi over 4. 3i cancel out, and we get theta equals pi over 2. Awesome. That's nice. Because we know r, we know theta. Why not put it together? Z is equal to r e to the I theta, which is 2e to the I pi over 2. What is e to the power I pi over 2? It's just pi, isn't it? So this becomes 2 pi. In other words, z equals 2i is a solution. And let's talk about why. If you take 1 plus I and square it, you get 2i. In other words, the square root of 2i is 1 plus I, and again, I'm talking about the principal square root. And if you plug it in, z root z becomes, what is z in this case? 2i, and root z is 1 plus I. You get 2i plus 2i squared, but I squared is what? -1. You should know this, right? So we get -2 plus 2i, which is what we're supposed to get. So, nice. Z equals 2i is a solution. However, is there another solution? That's the million-dollar question. And that'll be answered inside the second method. Let's go ahead and talk about the second method now, because I think that'll clarify things, hopefully. So now we have this equation, right? And notice the presence of square root of z kind of calls for squaring both sides, doesn't it? I mean, at least it should work. And when you square this, you get z squared. When you square this, you get z. Z squared times z is z cubed. So this becomes z cubed when squared. And when you square the right-hand side, you get negative 2 squared minus 2ab, which is 8i, minus 8i, plus 4i squared, which is minus 4. 4 cancels out. We end up with z cubed equals negative 8i. Beautiful. And I can write negative 8i as 8 times e to the power negative I pi over 2, because negative pi over 2, remember, is going to be the argument, right? Here's negative 8i. The argument is either you go 3 pi over 2 or negative pi over 2. Of course, when you take the square root, you kind of need to be careful because the principal square root is going to lie in a half plane, which is on the, what is it called? I don't know. You've seen it, so that's what it looks like. Or we can do this. We can go ahead and first add 8i to both sides. And then notice that 8i, I cubed is negative I, so I is negative I cubed. You can replace the I with negative I cubed, so this becomes z cubed minus 8i cubed. Get the idea? Now this looks like difference of 2 cubes, doesn't it? I mean, you can write it as follows, right? Like this. And then you can factor it using difference of 2 cubes. You remember the formula? It's a minus b, this is a, this is b, by the way, times a squared plus minus plus 2, not 2ab, just ab, so 2iz plus b squared, which is negative 4. Awesome. And then set it equal to 0. From here, you immediately get z equals 2i. You could also get z equals 2i, by the way, if you square rooted cube rooted both sides here. But you got to remember, any complex number has 3 cube roots, sorry, except for 0. 0 is very exceptional. Okay, let's go ahead and take a look at the solution of this equation because that's more interesting. Go ahead and solve it using the quadratic formula. You're going to get negative 2i plus minus the square root of negative 4 plus 16, which is 12. And that can be written as 2 root 3, right? And if you divide everything by 2, you get z equals plus minus root 3 minus I. Interesting. The plus minus is not in the middle. It's separated, or it's in the beginning. Okay. So we can kind of write these as follows. We're getting different solutions. Why didn't we get these with the first method? Maybe I missed something. Can you find out? Maybe I should use another angle or something like that. But these are candidates. You always check the solutions because there are potential solutions. And guess what? This one does not satisfy the original equation. If you plug it in, you're going to realize usable from alpha if you want. But this one checks, it works, and I checked it for you. And sometimes extraneous solutions arise because of squaring both sides. Now let's take a look at this. This is interesting, right? Look at the second solution. You can write it as follows. And then you can kind of write this as 2 times e to the power 7i pi over 6, okay? And then this is just z, right? What about the square root of z? Okay, cut the angle in half. You're going to get square root of 2 multiplied by e to the power 7i pi over 12, right? So this is basically the 7i pi over 2. And then, so there's 2 options here. Let me show you what I mean by that. 7i pi over 12 is going to be greater than pi over 2. So it's not going to be where we want it. Remember, we want our square roots to be here in order for them to be the principal square root. In other words, with a positive, what is that called? Positive real part, yes. So instead of this, I'm going to add pi to this and use 19 pi over 12. In other words, I'm going to write it as root 2 times e to the power negative 5i pi over 12. Basically, how I found that is subtracted 2 pi from it because I want it to be a negative angle, okay? It's going to be in the 4th quadrant with a negative angle. And if I put these two together now, z root z is going to be 2 e to the power 7i pi over 6 multiplied by root 2 times e to the power negative 5i pi over 12. Now, at these angles, this is 14 minus 5 is 9I pi over 12. 9I pi over 12 can be written as 3I pi over 4. When you multiply these, you're going to get 2 root 2 times e to the power 3I pi over 4. And if you remember, that is exactly negative 2 plus 2i, because at the very beginning, we wrote it that way. So that solution satisfies the equation. But why didn't it come up with the first method? That's for you to find out. And this brings us to the end of this video. Well, thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.